Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Here is the essay. Introduction. The 1797 work, authored by Caspar Wessel, titled On the Analytical Representation of Direction, an attempt, represents a pivotal moment in the evolution of complex numbers and their geometric interpretation. This essay will undertake a rigorous, section-by-section evaluation of Wessel's paper, meticulously scrutinizing its core claims, the methodologies employed, and the internal consistency of its arguments. The objective is to assess the validity and enduring significance of Wessel's contribution within the context of its own presentation. We will investigate the logical foundations of his reasoning, examining the evidence presented, and illuminating his conceptual frameworks. The intent is to offer a scholarly reflection upon the paper's integral elements, rather than any external comparisons. The focus will remain exclusively on Wessel's own words and the mathematical landscape he constructed. Section 1: Foundational Principles and the Representation of Lines. Wessel's exposition begins with a consideration of fundamental principles. His opening premise involves the representation of direction. He argues that a straight line with a given direction can be analyzed through the use of its length and its angular orientation. This is a crucial starting point, as it lays the groundwork for his subsequent algebraic manipulations. He suggests that two lines can have the same direction if each is parallel to the other. This foundation allows the construction of a system where direction equates to an angle measured relative to a fixed reference line. It is within this framework that Wessel plans his analytical representation of direction. He defines a unit of length, and through this, all other lengths are then expressed as multiples of this unit. His initial discussion provides a clear and understandable basis for his method. The paper clearly establishes a framework that links geometrical concepts with an algebraic method. Section 2: Addition, subtraction, and the geometric interpretation. Wessel then elucidates his operations of addition and subtraction, introducing the crucial concept of geometric addition for lines. He posits that the sum of two lines, when considered with respect to direction, can be achieved by placing them intoned. If line A is added to line B, the resultant line is the line from the point of origin of A to the end point of B, where B starts at the end point of A. This geometric method of addition is foundational for the rest of the paper. The subtraction operation is then construed as the inverse of addition. He meticulously defines the geometric equivalent of subtracting a line as equivalent to reversing its direction and adding it. He demonstrates the commutative and associative properties of this geometric addition. Mirroring the rules of ordinary arithmetic, Wessel carefully connects the algebraic operations with specific geometrical processes. This section serves to clarify the connection between algebraic and geometric forms. Section 3: Multiplication and the rotation of lines. The section on multiplication represents Wessel's most groundbreaking contribution. He establishes the rules for multiplying lines. The central insight is that when multiplying, a line must alter in length, and it must simultaneously rotate. Wessel states that the product of two lines with a given length and direction is a line whose length is the product of the component lengths and whose orientation is the sum of the component angles. He illustrates this rule with a series of specific examples. The crucial element in his formulation involves the concept of a unit line 1 with a length of 1 and an angle of 0. Wessel then introduces the notion of a unit line rotated by 90 degrees, which then creates a fundamental basis for the complex plane. This rotation by 90 degrees becomes the basis for what would later become known as I, the square root of -1. It is in this section that the true power of Wessel's analytical methodology is fully realized. He shows how multiplication, a seemingly simple operation, can be interpreted geometrically as a combination of scaling and rotation. Throughout this exposition, Wessel displays a remarkable intuition. Section 4: The fundamental equation and root extraction. Wessel subsequently turns towards a precise expression of the multiplication process, leading to a critical equation. Using the multiplication principle detailed in the previous section, he writes the correlationship using terms that relate to the length of a line and the angle it creates with a chosen reference line. The equation, in essence, is the analytical translation of the geometric operation. He demonstrates how it applies to various scenarios, reinforcing his geometric method with algebraic formalism. Furthermore, Wessel addresses the important problem of root extraction. He shows how taking the nth root of a complex number involves both scaling the length and dividing the angle by n. This demonstration is not just a mathematical manipulation, it is a direct consequence of his understanding of the geometric nature of complex number multiplication. His approach is both elegant and logically consistent, demonstrating how his framework can handle complex mathematical operations. Section 5, extending the system and the representation of curves. Wessel expands his system to encompass a broader range of geometric problems. He demonstrates how his analytical framework can be used to represent curves and perform calculations pertaining to them. He illustrates this through the creation of simple shapes, illustrating how his method can be used to analyze and calculate areas or perimeters. He shows how any point in the plane can be uniquely defined using complex numbers. He is able to show how the fundamental operations on complex numbers provide for the creation and manipulation of geometric figures. Wessel thereby establishes the connection between algebraic operations and specific geometric representations, the link between the abstract and the concrete. Section 6, criticisms and the nature of imaginary quantities. In addressing potential criticisms, Wessel confronts the fundamental question surrounding imaginary quantities, recognizing that his method involves the use of the square root of -1. He anticipates common reservations about the validity of such concepts. He asserts that the geometric interpretation of imaginary quantities provides a concrete validation for their employment. The square root of -1, for example, is not just an algebraic construct, it is a rotation of 90 degrees. He suggests that the geometrical framework resolves prior ambiguities and offers a system where imaginary quantities possess a clear and consistent meaning. Wessel directly confronts the prevailing skepticism related to complex numbers. Section 7, applications and the versatility of the analytical representation. Wessel spends time discussing the practical applications of his new system. He suggests that his method can be used to solve geometric problems related to triangles, quadrilaterals, and other shapes. He demonstrates how previously complex calculations can be significantly simplified. Wessel shows how to construct geometrical figures and how to find the area. He touches on the possibility of solving various problems in navigation and surveying, where direction and distance are key elements. Furthermore, he hints at the potential to extend this system to three-dimensional space, anticipating future developments. This section highlights the versatility of his analytical representation, demonstrating its power to solve a broad range of problems. Section 8, coherence and limitations of a general. Wessel's treatise then considers the limitations of his work. He acknowledges that this framework has certain specific drawbacks but insists that his method is applicable for the majority of geometric problems. His insights establish a clear understanding of the system's limitations and scope. Wessel establishes a sense of humility. This section provides a strong argument for the solidity of the mathematical logic. Section 9, conclusion and the enduring significance. Wessel concludes by summarizing his accomplishments and reinforcing the key ideas presented in his paper. He restates the principle of geometrical representation of lines and direction and the rules of operation for addition, subtraction, multiplication, and root extraction. The result is a cohesive, self-contained system based on a solid foundation. He underscores the fundamental connection between algebraic operations and geometric transformations. His final conclusion emphasizes the power of his method to simplify and solve geometric problems. The reader is left with an appreciation for the elegance and utility of his system. Conclusion: the enduring significance of Caspar Wessel's 1797 paper on the analytical representation of direction, an attempt, lies in its groundbreaking contribution to the visual and analytical understanding of complex numbers. The detailed examination of his work has revealed an internal coherence, marked by deep integration between geometric intuition and algebraic formalism. Wessel's innovation, presenting complex numbers as linear segments with both a length and an angle, offered a novel and fundamentally important perspective. His interpretation of multiplication as a combination of scaling and rotation gave rise to unprecedented opportunities for exploring geometric relationships. Further, his explicit formulation of the square root of -1 as a rotation of 90 degrees provided a profound and intuitive foundation for understanding these previously abstract mathematical concepts. The rigorous evaluation has demonstrated that Wessel's claims, consistently developed and logically sound within his own established framework, were not only internally consistent but also prescient, anticipating future mathematical developments. He did not just present a novel system, he provided a new language. His work provided the means for the visualization of fundamental mathematical and geometric concepts. The paper's impact can be traced in the subsequent development of complex analysis, its application to diverse fields, and the very language that mathematicians then used to express such concepts. The ideas presented in this paper serve as a basis for later explorations by mathematicians of his era and of the coming generations. Wessel's approach, though initially unrecognized by the broader mathematical community, proved to be a crucial catalyst in understanding and representing complex numbers. The significance of his work resides not only in his specific results, but also in his underlying vision, his capacity to link abstract ideas with visual intuition, and his pioneering efforts in establishing a new way of representing and interpreting mathematical relationships. Wessel's paper stands as a testament to the power of careful thought.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.